Hello everybody, welcome to my YouTube channel. My name is Thomas and today we'll be going through the proof of a very fundamental theorem in calculus called the chain rule theorem. Apparently there's a lot of people who don't know how to prove it, but without further ado, let's get straight to the proof. Before we do the proof, let's recall the definition of a derivative. So the definition is as follows. The derivative of f at a equals limit delta x approaches 0, delta y over delta x. And this is just the definition of the derivative, so there's nothing to explain or debate. But from this simple definition, there's a few results that we can see, and one of them, for example, is when delta x is very small, the derivative of f is approximately equal to delta y over delta x. Approximately and not exactly. And taking this into consideration, we can write the derivative of f at a is equal to delta y over delta x plus an error term, which we denote by epsilon 1. And since the derivative is defined as the limit of delta y over delta x, we know that as delta x approaches 0, our error term, epsilon 1, approaches 0. Okay, but doing a little manipulation, we see delta y over delta x equals the derivative of f at a minus epsilon 1, and then, delta y equals derivative of f at a minus epsilon 1 times delta x. So, in effect, this equation gives us the relationship between the increment using the error term and the derivative. Okay, remember this equation, it's important. It applies for anything that's differentiable, and we're going to use it a lot of times in this proof. Alright, next step, let's look at our composite function. It's defined as f of g of x. Now, for simplicity, let us denote g of x by u so that things look easier and prettier. Okay, now we get f equals f of u. Okay, so if we think of u as an independent variable, and we think of f not any longer as a composite function, but just a function of u, alright, then the increment of f would be, and we're going to use this relationship here, it would be equal to the derivative of f at, say, u. But, alright, so let g of a equal u a. Then the increment of f would be equal to f's derivative at u of a minus an error term, and we're going to use epsilon 1 to denote this one, multiplied by u's increment, delta u. But similarly, since u is equal to g of x and is in fact a function of x, we also know the relationship between the increment of u and the increment of x. And the relationship is this. Delta u equals the derivative of g at a minus error term, and since these two error terms are different, so I'm going to use epsilon 1 to denote the first one and epsilon 2 to denote the second one. Let me erase that quickly. Alright. The derivative of g at a minus epsilon 2 multiplied by delta x. Alright, and substituting this equation into this one, we get the increment of f is equal to the derivative of f at u of a minus epsilon 1 multiplied by g's derivative at a minus epsilon 2 times delta x. See, Now we have the relationship between the increment of the composite function and the increment of x. And this, in fact, allows us to compute the derivative because the derivative of f at a equals limit delta x approach 0, the increment of f over the increment of x, and which equals delta x approaches 0. This whole long sequence, we're just going to substitute it in. Sorry, it's a little squished up. I'm going to write it again. And we can cancel out the delta x's, and then this equals limit delta x approach 0, f derivative ua minus epsilon 1 times g derivative a minus epsilon 2. And but we know as delta x, since epsilon 1 and epsilon 2 are both error terms, as delta x approaches 0, epsilon 1, epsilon 2 both approach 0. And so the derivative of f at a equals these two multiplied together. And remembering that u is just g of x, this equals g of a, g's derivative of a. And since we chose a to be any arbitrary number, we can now substitute a out and replace it with x, the variable. And this is the final result. So we have successfully proved the chain rule theorem.